So, all right. So, now that the principles are covered, we can move on to the next topic. Any questions? Yes. Which? On the right side of the green, in the above. Okay. Yes. The infinite capacitor should be connected in series with RS. Oh, sorry. Indeed. Thank you very much. Sorry. Hey, sorry. Yeah. Indeed. Yeah. Thank you. I hope that's I have not made a blunder anywhere else. Yeah, that's fine. Thank you. Okay. Very good. So, now let us move on to the next topic, which let me motivate the topic for you. Remember that when we wanted to make a good voltage amplifier, things like that, we basically wanted to use feedback to make the input output properties of the amplifier independent of the properties of the active elements, correct? And the ideal thing would be, of course, therefore, if we go back to our negative feedback block diagram. So, we have some input and we have some output which we feed back, and we said that the closed loop VO by VI will tend to 1 over F if A tends to infinity, correct. And then we said, well, we actually will be able to sell that part as a building block where users can go and put their favorite feedback factor and get whatever closed loop gain they want. So, and therefore, what the operational amplifier, this was the operational amplifier, and what the operational amplifier was doing was basically taking two voltages Vx and Vy and generating VO equals Vx minus VO is A times Vx minus Vy, where A tends to infinity. All right. And so, the first step in the process, therefore, I mean, presumably with finite lambda of the transistors or non-zero lambda for the transistors, it is not possible to get a large gain with one stage, right. I mean, which amplifier do you think is the most useful candidate to get a large gain among all the common source, right, and perhaps with an active load, so that you get as much gain as possible in a small supply. Now, but here and presumably with one stage you cannot get I don't know, I mean typical gains for operational amplifiers are maybe 10 power 4, 10 power 5, that kind of thing, and therefore, it is not possible to get it in one stage. So, you have to cascade stages, and on top of it here the common source amplifier we saw gave us gain. So, it is presumably we need to cascade several of these common source amplifiers to get, I mean, if each common source amplifier can give us only a gain of say 100, then, and if you want 10 power 4, then you have to at least cascade 2 stages, right. If on the other hand the single stage gives us only a gain of 25, then you have to cascade I don't know more stages. So, it is a given that we have to cascade high gain stages to get a really high gain for the operational amplifier, right. However, there is a slight difference. The difference between the common source amplifier we know, right, and what the operational amplifier is supposed to be doing is the following. The operational amplifier is is amplifying only the difference between Vx and Vy, right. And our common source amplifiers that we have seen so far are just amplifying one input, that small signal input Vi that we are giving, they are just amplifying that with presumably a large gain. If you want an even larger gain, you take another common source amplifier and cascade it with the first one, correct. But what is called for, we also need therefore a building block whose job is to only amplify the difference between two voltages. Does it make sense, right? And the motivation, why we need this is because in an operational amplifier, that amplifier is only concerned about the difference between Vx and Vy. So in other words, whether Vx is if Vx and Vi are 1 millivolt and 0, or whether Vx and Vi are 100 volts plus 1 millivolt and 100 volts, the output of the operational amplifier must be the same. Okay. So in other words, what we are interested in is finding a building block that amplifies only the difference between two voltages, let's call that Vx and Vy. All right. So, and again, so what is the simplest thing? So, we already know the common source amplifier, we know the transistor, how it behaves, right. One way to think about it is to say that, well, the transistor responds only to the difference between the gate voltage and the source voltage. So, hey, how about, why not put Vx here and Vy there? For sure, this only depends on Vx minus Vy, because if Vx and Vy both increase by exactly the same amount, the transistor does not know anything. It just, since it only reacts to Vx minus Vy, right. But there is a small catch here. Remember that in a good negative feedback loop, what comment can you make about the difference between Vx and Vy? Let us assume that we make this all work, right, and we indeed have a great operational amplifier, right. Once you embed the operational amplifier inside a negative feedback loop, what did we discuss would be the difference between the voltages Vx and Vy? Negative feedback is going to force that difference to be ideally 0. In reality, it is going to be a very, very small voltage, where that smallness depends on how large the loop gain is. Is that clear? So, if we succeeded in making the operational amplifier after all, right, we should expect that Vx and Vy will be very close to each other. Ideally, they will be identical. So, if Vx and Vi are very close to each other, and then you put one at the gate and one at the source, what comment can you make about the transistor? If Vx and Vy are identical, what comment can we make about the region of operation of the transistor? The transistor is cut off, right. So, that is basically evidently a contradiction, right, because we want high gain between high incremental gain Vx minus Vy to be amplified by a large factor, but if Vx and Vy are the same, the transistor is actually off. Okay. All right. So, in other words, what we need, what we need definitely is that the transistor must not be off when Vx is equal to Vy. The transistor must be in saturation, carrying some current, correct. So, in other words, the gate source voltage when Vx is equal to Vy must be it must be carrying some current, which basically means that must be some Vt plus some overdrive, right. Let me not confuse you with delta V. What do we call this? Okay, let me call this here. This is the overdrive voltage. Does it make sense? So, when Vx is equal to Vy, we want to make sure that the gate voltage is the transistor is alive and is actually carrying some current, so that the gate source voltage is greater than the threshold by an amount delta V. Is that clear? So, then so therefore, what comment can you make about this voltage therefore? When Vx is equal to Vy, Vgs must be equal to Vt plus delta V. So, what voltage must we put at the, so this voltage must be Vy minus Vt plus delta. Correct? Alright. So, under those circumstances, what comment can you make about the drain current of the transistor? I will be equal to half mu n Cox W by L times Vgs, which is Vx minus Vy plus Vt plus delta V minus Vt. So, this is Vgs, this is Vt the whole square, alright. So, which is therefore half mu n Cox W by L times delta V, sorry, this is Vx minus Vy plus delta V the whole square, alright. So, now what comment can you make about if Vx minus Vy is a small quantity, right? Ideally, we know that that is going to be almost 0. So, what comment can we make about di by d Vx minus Vy? This is a small quantity. So, now if Vx minus Vy changes by a little bit without writing any equations, what that is nothing but what is that quantity mu n Cox W by L delta V? Is the GM of the, I mean, this is basically saying I am changing the gate source voltage by a small amount. What is the change in the drain current? It is nothing but Gm times Vx minus Vy. Is this clear? Is this clear now? So, at this point, so when if at the source rather than applying Vy, we applied Vy minus Vt plus delta V, you know, we are the transistor still responds to only Vx minus Vy, alright, and for small changes in Vx minus Vy, the change in the drain current of the transistor is Gm times Vx minus Vy. To get a large gain which is only dependent on Vx minus Vy, therefore, what will we continue to do? How will we convert this change in drain current into a change in voltage? Why are they not this is Gm, okay, fine. How will we convert this small difference into a voltage? Where will we put the resistor? In the drain. I mean, this is exactly the same thing as a common source amplifier, except that there we had the source connected to ground and we applied the voltage to be amplified at the gate. Now, what are we doing? we recognize the fact that the source, the transistor only responds to the difference between the gate and the source voltage. So, we apply one of the voltages at the gate, the other one at the source. If you directly apply the other voltage at the source, if I find that we end up with a contradiction because the transistor is going to be off. So, to keep the transistor alive, what we must apply at the source is not the second voltage Vy itself, it must be minus Vt plus some over. Okay. Now, the question is, how do I generate from Vy, how do I generate Vy minus Vt minus delta V? What is the simplest single transistor circuit that you can think of? You put Vy there, what you want is Vy minus Vt minus delta V. What single transistor circuit can you think of that can accomplish this? In your mind, go over all the single transistor circuits that you know. We need a box, okay. This is a box. We want to get Vy minus Vt minus delta V, correct. So, if Vy changes a little bit, what comment can you make about the output? This is a box, okay. We are trying to figure out what there is inside the box. Please answer the question that you are asked. What is the output? Vt minus delta V. Okay. Now, if I change the input by a small amount, how much will the output change by? By the same small amount, correct. So, what is the incremental gain? 1. Okay. So, can you think of a simple single transistor circuit which has got an incremental gain of 1? The common drain amplifier. Is this clear? Okay. So, basically, how do we generate this? This guy here? Well, we take let me just call that 2I0 for turns out that it becomes convenient, nothing else, we could have called it I0. Okay. So, what happens now? What should we do? What is that voltage? Assume RO is infinity. Yeah. So, basically the voltage drop across the gate source is dependent on that, on the size of the transistor and the current that you are pulling through it, correct. So, the voltage is that voltage at the source of the second transistor M2 is some Vy minus some Vgs of M2, okay, all right. And I will choose M2 to be equal to the size of M2 to be equal to M1, right. And so, what should I do now? What is the next step? So, what I do is basically connect this there. Okay. So, if I draw it slightly differently, basically the same thing drawn in a neater fashion. This 2I0, this is Vx and this is Vy, okay, and you put a resistance R there, right. So, this will give you what is the incremental voltage. If Vx minus Vy is very small, there is some Gm times R, negative Gm times R, right. If you want positive Gm times R, what will you do? Yeah. So, basically, I mean, this whole situation is symmetric with respect to, if you put an R there, then it is symmetric with respect to whether you want to find Vx minus Vy times A or Vy minus Vx times A. So, if you put a resistor in both drains, then you will have the same incremental output with opposite sign depending on which drain you tap, okay. So, this is the so called differential play or differential amplifier. So, this part you understood. What is the incremental voltage here? So, minus Gm times R times, what is the incremental voltage there? Okay, let us go back here. Okay, so, this voltage is, I mean, if this voltage was Vy minus some Vt minus delta V, what will be the incremental voltage here? Minus GMR times Vx minus Vy, correct. So, that will give you the negative of, it will give amplified, here is an amplified version of the negative of Vx minus Vy, okay. So, now if you want a positive version, what will we do? I mean, notice the stuff below, it is perfectly symmetric, right. So, basically instead of putting the resistor on the left side, if you put it on the right side, then what will you get? Put on the right side, what will you get? What is the difference between, so let us say you just saw this part, what is the difference between that guy and this guy here? Pardon? We are just interchanging x and y, correct? Do you understand? So, if you take the output at the drain on the right hand side, you will basically get something which is proportional to negative of Vy minus Vx, which is simply the inverted version of Vx minus V. Is this clear? So, that is the intuition behind how this, how we are able to amplify only the difference between Vx and Vy, okay. So, if Vx and Vy both go up by 1000 volts, alright, as long as you are able to keep all the transistors in saturation, nothing in principle should happen to the incremental output, because the transistor only reacts to difference between Vx and Vy. Is that clear? Okay. So, now let us start doing careful analysis. Now, a little bit of notation. So, Vx and Vy are expected to be very close to each other. I mean, they will be same only if the gain of the amplifier is, of the operational amplifier is infinite. in reality the gain is never infinite, it is only a very large number. So, that Vx and Vi are going to be different, but the difference is going to be small. So, so it is more convenient to express the outputs, the inputs Vx and Vy as Vx plus Vy by 2 plus Vx minus Vy by 2 and Vx plus Vy by 2 minus Vx minus Vy by 2. Okay. So, instead of saying I do not know 10.01 volts and 10 volts, you say well 10.05 volts is the average of the two and one is a small amount more than the average, the other one is small amount less than the average. Okay. And this has got nothing to do with circuits, this is just a way of expressing two numbers in a different form. Okay. So, this is called the this is the part which is common to both Vx and Vy. So, this is called the common mode component, okay, which is often called VCM, and this is the differential mode component, which is called we are going to you can call it VDM, but I dropped the M. So, this is nothing but VCM plus VD. We deliberately write the differential mode as in smaller case, just to keep reminding ourselves that the difference between the average can be anything, right, but the difference is always small, okay, and this is VCM minus VD. All right. So, in other words, this is VCM plus VD, this is VCM minus VD, all right, and what we are interested in is how the voltages say here and here depend on VD. Okay. We already saw that it does not depend on VCM, it only depends on VD. So, well so if you think about it as a as a circuit problem, circuit analysis problem, VD is a small signal, right. On one side it is VCM plus VD, other side it is VCM minus VD. To find the response to VD, what do? VD is a small signal, here is a nonlinear circuit, what will we do? What are we trying to do? We find the first job is to find the operating point. So, to find the operating point, what will you do? You say you set the small signal component to 0, correct, and then find the node potentials. So, basically the operating point calculation is very straightforward. This is some capital VCM this is 2I naught, this is R and VD. So, to find the operating point, what is the first thing that strikes you when you look at this circuit? It is symmetric, right. So, basically what will be the current flowing through M1? So, the current flowing here is I naught. So, what will be the what is the quiescent voltage at the drains? VDD minus I naught times R. what is the quiescent voltage at the source? Source VCM minus VGS, which is what? VT plus delta V, which is basically square root of 2 I naught by that mu and C ox blah blah. Is that clear? Okay. So, first question, what is the largest VCM that will make sure that the transistors M1 and M2 are in saturation? By the way, why do we want them, why do we want M1 and M2 to be operate in saturation? You will get a large gain, incremental gain. So, the maximum, so obviously as you keep increasing VCM, right, are the transistors M1 and M2 going deeper into saturation or closer towards the triode region? Closer towards the triode region, because the drain potential is remaining constant, the gate potential is going on increasing. So, they are going closer and closer to the triode region. So, there must be a maximum input common mode voltage you can use before the transistors go into the triode region. And so, what is that VCM max? Very good, VDD minus I naught R plus VT. Okay. And how are we going to realize this current source? Current mirror with what? So, you put a all right. So, for example, so here is M3, M4, let me call this 2 I naught, all right. This I will call delta V, let me call this W by L, W by L, I will call this W by L, this is 2 W by L. So, when the transistor, when VCM is becoming lower and lower, what happens? What happens? The drain potential of M4 is VCM minus VT minus delta V, correct. So, as VCM goes on decreasing, M1 and M2 are okay, but M4 is going towards the triode region. So, what is the, so as you keep lowering the input common mode voltage, which transistor gets into trouble, has the potential to get into trouble? M4. So, what is the minimum common mode voltage that you can use before something bad happens? It is delta V, is that clear? Okay. So, this is delta V. So, then what is the minimum common mode voltage VCM? The source voltage is at delta V. So, what must the gate voltage of M1 and M2 be, so that the source voltage is at delta V? So, the gate source voltage of M1 and M2 is nothing but Vt plus delta V. So, the source is at delta V. So, what is the minimum common mode input voltage? Vt plus 2 delta. All right. So, therefore, there is a the actual VCM must be greater than a certain minimum and less than a certain maximum. This is called the common mode range. All right. Okay. So, if the input common mode voltage is in the common mode range, right, then both M1 and M2 are guaranteed to operate in saturation. Okay. So, that basically is the we have done, therefore, we are done with the operating point. So, let us revert to our original